Today, our topic is about acid-base titrations. What are titrations for? Titrations are procedures in which one reactant is slowly added into a solution of another reactant, while equilibrium concentrations along the way are monitored. So there are actually two main reasons why we do titrations. First is to determine the concentration of one of the reactants, and the next is to determine the equilibrium constant for the reaction. So in an acid-base titration, a solution containing a known concentration of base is slowly added to an acid, or the acid is added to the base. Now in this discussion, we are going to consider three types of reactions for acid-base titrations. And these are the following. First is the strong acid versus strong base titrations, and then weak acid versus strong base titrations, and strong acid versus weak base titrations. Let us first discuss some terms. First is the equivalence point. This is the point at which stoichiometrically equivalent quantities of acid and base have been brought together or have been reacted. So for acid-base titrations, just like any titration, indicators can be used to signal equivalence point. Alternatively, a pH meter can also be used to monitor the progress of the reaction, producing a pH titration curve. Now, what then is a pH titration curve? A pH titration curve is a graph of the pH as a function of the volume of titrant added. Now, the shape of the titration curve makes it possible to determine the equivalence point. So the curve can also be used to select suitable indicators and to determine the Ka of the weak acid and the Kb of the weak base being titrated. So here is an example of a pH titration curve. So the reaction is between a strong acid and a strong base as represented by this equation. So suppose we have reacted sodium hydroxide as our strong base and hydrochloric acid as our strong acid. So here in this titration, the titrant is the strong base, which is sodium hydroxide, and the analyte is hydrochloric acid as our strong acid. So this is an example of the general shape of the pH titration curve when a strong base is added to a strong acid, which depicts the pH change that occurs as, for example, a 0.100 molars NaOH is added to 25 ml of 0.1 molars hydrochloric acid. So the pH can be calculated at various stages of the titration. So to help us understand further about these calculations, we will be dividing the curve into four regions. So in the titration of any strong base with any strong acid, these are the four regions. So initial pH, between initial pH and equivalence point, or before equivalence point, and then equivalence point and after equivalence point. But there are actually three main regions of that titration curve that will require different kinds of calculations. So these are before equivalence point, at equivalence point, and after equivalence point. But before doing any calculations, let us first understand each of these four regions in the pH titration curve. Initial pH. So this is the pH of the solution before adding any base or any titrant, and is determined by the initial concentration of the strong acid. So since what we are titrating is a strong base and a strong acid, the initial pH is low, okay, or the solution is acidic since that is our analyte. So let's say we have 0.1 molars hydrochloric acid, then the hydrogen ion concentration is also 0.1 molar, which makes the pH to be 1. So that is our initial pH. And then between initial pH and equivalence point, or let us just simply say before equivalence point. So this is the pH before equivalence point is determined by the concentration of acid not yet neutralized. So as a strong base is added, so as you can see from here, our initial pH is 1, right? So as we slowly add acid, for example, sodium hydroxide, we can see that the pH slowly increases also at first. And then as it nears the equivalence point, it rapidly increases. So the pH before the equivalence point is determined by the concentration of acid that is not yet neutralized. Now we discuss the third region, or the region at equivalence point. So at the equivalence point, an equal number of moles of sodium hydroxide and hydrochloric acid have already reacted, leaving only a solution of their salt, which is sodium chloride. So here we have this one as our equivalence point. So the pH of the solution is 7 because the cation of a strong base and the anion of a strong acid are neither acids nor bases, and therefore have no appreciable effect on pH. Now, what about after equivalence point? So pH is determined by the concentration of excess sodium hydroxide in the solution. So always remember that after equivalence point, the major species already, okay, that will determine the pH of the solution would be the titrant, or the sodium hydroxide, or the strong base. So the pH of the solution is determined by the concentration of the excess sodium hydroxide or hydroxides in the solution. Now let us get to calculations. It is possible to calculate the pH of the solution at every stage of titration. So let us have some examples. In the previous slide, we have already seen that at initial pH, the pH of the solution is equivalent to the pH of the strong acid. That is true when the type of titration is between strong acids and strong bases. So now let us again consider the addition of 0.1 molars sodium hydroxide solution to an Erlenmeyer flask which contains 25 ml of 0.1 molars hydrochloric acid. So what will be the pH after the addition of 10 ml of the titrant? So after the addition of 10 ml titrant, the total volume of the solution is now 35 ml. So initially we have 25 ml, and then afterwards we will be adding 10 ml of titrant. So the total volume is 35 ml. And then after that, we have to determine the total number of moles of sodium hydroxide in the solution, or in the 10 ml titrant that was added. So in order to calculate for that, we will be using dimensional analysis. So we start with the initial volume of sodium hydroxide that was added, which is 10 ml, and then multiply that with the concentration of our base, which is 0.1 molars, and then we will be able to get 1.00 times 10 raised to negative 3 moles of sodium hydroxide. Now that we know the number of moles of sodium hydroxide, our next step is to find out the number of moles of hydrochloric acid. Okay, yung initial hydrochloric acid that we have, which is 25 ml, multiply that with the concentration of the strong acid, and we will be able to get 2.50 times 10 raised to negative 3 moles. After that, we will be subtracting the two from each other. So we will be subtracting the moles of sodium hydroxide from the moles of hydrochloric acid. Now, why do we need to subtract? Hydrogen ions and hydroxide ions would react to form water molecules for the neutralization reaction. Okay? So that means that what we will be having after the hydrogen ions and the hydroxide ions have reacted with each other, the amount of hydrochloric acid left after that partial neutralization is 1.50 times 10 raised to negative 3 moles. So this means that before equivalence point, the major species that will be in our solution is actually hydrochloric acid, and that will determine the pH of the solution. Okay, so after this, we can calculate for the molarity, or the concentration of hydrochloric acid, and we will be able to get 0.0429 molars of hydrochloric acid. Since this is a strong acid, this will also be the concentration of the hydrogen ions in the solution. So now we can calculate for the pH, and we will simply use the equation pH is equals to negative logarithm of hydrogen ions, and so we will be getting 1.37 as our pH before equivalence point after the addition of 10 ml titrant into our acid. So that is how we will be calculating for pH before equivalence point. What will be the pH at equivalence point? So from the previous slide, we have already seen that at equivalence point, okay, so there are actually equivalent numbers or equal numbers of the hydroxide ions and the hydrogen ions in the solution. So this is a simple calculation because it will involve a complete neutralization reaction. And the salt or sodium chloride that will be formed does not undergo hydrolysis, so it will not affect the pH of the solution. So after the addition of 25 ml of 0.1 molars NaOH and zero point 0.1 molars of hydrochloric acid, the solution has already reached its equivalence point. So as we can see from the graph in here. So for the calculation, we will have equivalent numbers or equal numbers of hydrogen ions and hydroxide ions. So that will be 1.0 times 10 raised to negative 7 molars. Then the pH of the solution is 7. So this is true when the titration is between strong acid and strong base. Now, what about after equivalence point? What will be the pH? So suppose you have added 35 ml um, and the total volume now of the solution is 60 ml. So the total amount of titrant that has been added into the solution is 35 ml of 0.1 molars NaOH. So here, the major species in the solution are now sodium hydroxide and chloride ions. So by this time, all of the hydrogen ions are consumed and has been completely neutralized in the reaction. So now we calculate for the total number of moles of sodium hydroxide that has been added into the solution. So again, we will be using dimensional analysis. And from there, we will be able to calculate 3.50 times 10 raised to negative 3 moles of sodium hydroxide. And then let us now subtract um, the number of moles of hydrochloric acid from the total number of moles of sodium hydroxide. So now we have 1.00 times 10 raised to negative 3 moles of sodium hydroxide. So as I've said a while ago, the major species in the solution are now sodium hydroxide and chloride ions. So we will now be calculating for the concentration of NaOH, and we will be able to get 0.0167 molars of sodium hydroxide. So this will now determine the pH of the solution. Since what we now have in our solution is the base, then we expect that the pH will be basic or will be higher than 7. So then, the pOH is 1.78, so the pH of the solution is 14 minus pOH, and the calculated pH of the solution after equivalence point is 12.22. Now we will be focusing on weak acid versus strong base titrations. So for this titration, let us consider the neutralization reaction between acetic acid, which is a weak acid, and sodium hydroxide as our strong base, as described by this chemical reaction. So this equation can be simplified to the following. So we have here acetic acid plus hydroxide ion representing our strong base, and will give us this product as the acetate and water. The acetate ion undergoes hydrolysis and will have the following equilibrium reaction. For a weak acid strong base titration, since it involves a weak acid, so for this time we have acetic acid as our weak acid, so it undergoes equilibrium reaction. So we will also be needing the value of Ka to calculate for the initial pH. Okay. Now, before equivalence point, when the acid reacts with the titrant, its conjugate base is being formed. So for acetic acid, we have the following reaction. So in here, you can see the solution now contains a mixture of acetic acid and acetate ion. And so calculating the pH in this region involves two steps. So the first step, um, is we will be considering the neutralization reaction between acetic acid and the strong base or the hydroxide ion to determine the concentration of acetic acid and the acetate ion. And then after that, we will be calculating the pH of this buffer pair using procedures that we have discussed in buffer calculations. So the equivalence point is reached when we have equal number of moles of the weak acid and the strong base. However, the conjugate base that will be formed is a weak base whose reaction with water cannot be neglected. And therefore, the pH at the equivalence point will be greater than 7, unlike in the titration between strong acids and strong bases. So in general, the pH at equivalence point is for a weak acid strong base titration will always be above 7 because the anion of the salt formed is a weak base. In this region, so after equivalence point, we are already right here. The hydrogen ion concentration from the reaction of acetate ions with water is negligible relative to the concentration of hydroxide ions from the excess sodium hydroxide. So how will the pH be determined after the equivalence point? It will be determined by the concentration of hydroxide ion from the excess sodium hydroxide or our excess titrant. So how are we going to do the calculations? So treat the stoichiometry and equilibrium problems separately. Okay, since this both involves stoichiometry and equilibrium reactions. So for calculating the pH when a weak acid is partially neutralized by a strong base, we can use this calculation. So first, we have the solution containing the weak acid. After the strong base or the titrant is added, this is what happens. So a neutralization reaction proceeds wherein the weak acid decreases or the concentration of the weak acid decreases and the concentration of our conjugate base or our anion increases. Okay, so this involves a stoichiometry calculation. So we can now calculate the new values of the concentration of our weak acid and our um, conjugate base, so our acetate ion. And then after that, we can proceed with the equilibrium calculation. So we will be using Ka since it involves weak acid, and then concentration of the conjugate base to calculate for the concentration of the hydrogen ion, and then we can calculate for the pH. So for a weak acid strong base titration, this will involve two calculations, a stoichiometry and equilibrium calculation. So let us have this example. Consider the titration of a 50 ml of 0.10 molars acetic acid, which has the following Ka value, 1.8 times 10 raised to negative 5, with 0.10 molars of NaOH. Now, we will be determining the following. First is the initial pH, the pH before equivalence point, pH at equivalence point, and pH after equivalence point. Okay, so at initial pH, let us consider the titration of a 50 ml of 0.10 molars acetic acid, okay, which has the following Ka value. So for this, we will be using a typical weak acid calculation. So I have discussed this already in the previous video, so I will not be discussing the steps here anymore. So here, the pH that we will be able to calculate is 2.87. Now, before equivalence point, what will be the pH after the addition of 25 ml of the titrant? So let us begin solving the first part, which is the stoichiometry problem. The reaction is set up like this because the strong base hydroxide ion will react with the strongest proton donor, which in this case is acetic acid as our weak acid. So before the reaction, what we have is 2.5 millimoles of hydroxide ion and 5 millimoles of acetic acid. And then after the reaction, we will be subtracting. So what we will have left, or the major species that will remain after the reaction before equivalence point, is 2.5 millimoles of acetic acid and 2.5 millimoles of acetate ion. So the hydroxide ion has been completely reacted or neutralized with the acetic acid. After equilibrium is established, the major species in the solution are acetic acid, acetate ion, sodium ions, and water. So to represent equilibrium, we will be writing this chemical equation here, and then the corresponding calculations are as follows. So initial concentration, and here on the right side, we have equilibrium concentration. So initially, what we have is 2.5 millimoles of acetic acid, okay, over 50 ml plus 25 ml, since that will now be the total volume of the solution, okay. Same goes with the acetate ion. And then this will be the equilibrium concentration, or the setup for the equilibrium concentration. Okay, so now we will be setting up the ice table. Now that we have all these details, we can now substitute it into our equilibrium constant expression. Okay, so after substituting it into our equilibrium constant expression, so we will have this. Our Ka value is 1.8 times 10 raised to negative 5, and then substitute everything coming from our ice table, okay, under the equilibrium section, and then we will be able to get X, okay, which is the concentration of hydrogen ions, okay, which is 1.8 times 10 raised to negative 5. And so our pH before equivalence point is 4.74. Okay, and if you will notice, our concentration of hydrogen ions is actually equivalent also to the value of our Ka. So at this point, the solution contains the following major species. So we now have sodium ions, acetate ion, and water. So note that the acetate ion is actually a base. Therefore, it would want to combine with a proton. And from here, since the acid or the weak acid has completely been neutralized, the only source of proton in here is water. So therefore, the reaction will be as follows. So here we have the equation or the reaction between the acetate ion and water to produce acetic acid and hydroxide ion. So this is a weak base reaction characterized by Kb, so we will be having the following equilibrium constant expression. So this is just to show the expression and how the Kb is acquired. Now, these are the relevant concentrations. So at initial concentration before any acetate ion reacts with water, so this is what we have. The concentration of acetate ion is 0.015 molars, okay? No hydroxide ion and no acetic acid. And then after the change, okay, after it reacts with water, this will now be our equilibrium expression or the equilibrium concentrations. Now, what we need to do is to find out the value of X. Let us now set up our ice table. So our ice table would look like this. And then we substitute that into our expression to get the value of X. So we assumed that X is negligible, which is made valid by the 5% rule. So now that we know the value of X, which is also equal to the concentration of hydroxide ion, we can now calculate for pH. Okay, so from there, we can calculate for the hydroxide ion concentration, which is 5.3 times 10 raised to negative 6 molars. And then, okay, from there, we can get the hydrogen ion concentration from the Kw expression. Okay, hydrogen ion concentration is 1.9 times 10 raised to negative 9 molars. Therefore, the pH at equivalence point is 8.72. So remember that whenever the titration is between a weak acid and a strong base, the equivalence point would always be greater than 7. This is because the anion of the acid, which remains in the solution at the equivalence point, okay, is a base. So now let us calculate the pH after equivalence point. But first, bear in mind that at this point, excess hydroxide ions has already been added into our solution. So therefore, we will be doing stoichiometric calculations. And the major species in the solution are sodium ions, acetate ions, hydroxide ions, and water. And if you will also notice, there are two bases in the solution, which are hydroxide ions and acetate ions. Now, however, if we will be comparing the two, the acetate ion is a much weaker base compared to the hydroxide ions. So therefore, the amount of hydroxide ions produced by a reaction of acetate ion with water will be small compared with the excess hydroxide ion, which are already in the solution. So what will determine pH? It will be determined by the excess hydroxide ion. So therefore, the acetate ion concentration will be negligible in its effect to calculating the pH after equivalence point. Okay, so from here, we will be using the concentration of hydroxide ions, which is the millimole of hydroxide ions in excess over the total volume of the solution, which is 1 millimole divided by 60 plus 50 ml or 110 ml. And then we will be getting 9.1 times 10 raised to negative 3 molars. Okay, from there, we can calculate for the hydrogen ion concentration, okay, which is 1.1 times 10 raised to negative 12 molars, and then calculate for pH. So the pH of the solution after equivalence point is 11.96. Okay, so now let us go to our third consideration or third scenario, which is the titration between strong acids and weak bases. So titrations of weak bases with strong acids can be treated using the procedures that we have previously discussed. So as always, think first about the major species in the solution and then decide whether a reaction goes essentially to completion or not. So for this titration, we will be considering ammonia as our weak base and 0.10 molars hydrochloric acid as our strong acid titrant. So in this part, we will not be doing any detailed calculations anymore, but we will be discussing the processes. So first is the pH or initial pH. For any addition of the titrant, the major species in the solution are ammonia and water. So those are our major species. We know that ammonia is a base, so therefore it will seek a source of protons. In this case, water is the only available source. So no reactions occurred go to completion and an equilibrium is established, which will also control the pH. So here, we will be using Kb, okay, to calculate for the hydroxide ion concentration, and then pH can be calculated. So as compared to the titration between a weak acid and a strong base, at initial pH, we will be using the value of Ka. So this time, since what we have is a weak base, then we will be using Kb to calculate for the initial pH. Okay? Next is to calculate for the pH before equivalence point. So before that, let us take into account what are the major species before any reaction takes place. So here, the major species are ammonia, and then hydrogen ions and chloride ions from the dissociation of our strong acid, which is hydrochloric acid, and water. And then we take note that ammonia will react with hydrogen ion from the added hydrochloric acid and will be represented by this chemical equation. Now, after this reaction, the solution now has the following major species. So we now have ammonia, ammonium ion, which is formed in the titration reaction, chloride ion, and water. Take note that the solution now contains ammonia and ammonium ion, and the equilibria involving this species will determine the concentration of the acid or the hydrogen ions. So you can use either the dissociation reaction of ammonium ion or the reaction of ammonia with water. Now, how about after the equivalence point? So, excess hydrochloric acid has been added already, and the major species in the reaction are hydrogen ions, ammonium ions, chloride ions, and water. So the pH of the solution will be determined by the excess hydrogen ions from the hydrochloric acid titrant rather than the ammonium ion. So therefore, it will determine the pH.